Given a curve r, r of t, there are three vectors that are very important. The tangent vector corresponding to this curve at any given point, the normal vector, and the binormal vector. Those are unit vectors, by the way. Tangent unit vector, normal unit vector, and binormal unit vector. So they're going to give us directions, very, very important directions about the curve. So given a point, the tangent vector will be this kind of vector that goes in the direction in which the trajectory of this point would continue going if it wasn't because it is bending. So if this is curving, but then the moment you release the bending, the gravity, if you will, from this point, then the point would continue going straight. This direction is what the tangent vector does. So, and we label it as t. And it is a unit vector, which means it's pure direction. Unit vectors are pure direction. They don't have magnitude. Now, when I say they don't have magnitude, what I mean is that the magnitude is one. In other words, the magnitude is not going to tell us the velocity necessarily. It's just going to tell us a direction. The normal vector is the perpendicular vector to the tangent vector in the direction of the bend. So if the curve is bending downwards, as in this case, then the normal vector is going to go straight perpendicular to the tangent vector. And they are supposed to be the same length. Right now, in my picture, this looks a little shorter than this because I drew this by hand, but this vector should be the same length as this one, which is 1 unit. And this is called the normal vector at this point. If you pretend this is a portion of a circle, then at this point, the curve will be approximated by a circle. Then the direction of this normal vector points towards the center of that circle. It won't be the radius of the circle because this is a unit vector, so it is pure direction. It doesn't tell us too much about the magnitude, how far this is pulling in or not. And then we have the binormal vector, which would be the cross product of t crossed with n. In this picture, the binormal vector would be going according to the right hand orientation. It would be going away from us. There we go. And that is binormal vector. All three are unit vectors. The lengths are 1. And they are all perpendicular to one another. So this is perpendicular, and the binormal vector and normal vector are perpendicular, and so are the tangent vector and binormal vector. All of them are perpendicular to one another. So tangent, normal, binormal. So we start with r of t. The tangent vector is the derivative of r. That would give us this direction with the velocity. But then we got to divide by the magnitude. And that makes this the unit vector. So this is the formula for the tangent vector. Once you have the tangent vector, you can find the normal vector by, let's write it down here, taking the derivative of the tangent vector and then dividing by its own magnitude. So t prime of t. So derivative, make it unital, derivative again, make it unital, and that gives us those two. And then we have the binormal vector, which is the product, the cross product, t crossed n in that order, not n cross t, t crossed n. Very, very important. um, vectors defined by a curve. An interesting example would be what happens if we attempt to do the normal vector of a straight line, because a straight line does not curve. I'll let you do that on your own and see what happens. Yeah. Let's move on to an example. So example 1, find tangent unit vector, normal unit vector, binary unit vector for r of t, which is going to be cosine t, sine t, t over 2 pi. Interesting. The same kind of example. At t equals pi. By the way, when t is equal to pi, we will have -1. If you plug in t for the cosine of t, you end up with -1. Sine of pi will be 0, and pi over 2 pi is 1/2. Sometimes the book or any textbook or I will give you the t value at which we want to figure this out, the tangent, the normal, and the binormal vectors, or the point. So oftentimes we give you one or the other, given one or the other. Typically, we don't give you both, but sometimes we may give you both. So if we provide the point, then it is your job, it is part of the problem to figure out what t value triggers this point. If we give you t, it's not a bad idea to know what this is, but I don't think for purposes of simply finding those vectors, you'd need to find that. But if we give you this, then the problem becomes a little more complicated because we have to add the figuring out of t. Now, how difficult that is depends on the formula we're using. For instance, what I would do is just clamp onto this guy, because that is a linear function, and it is, in this case, 1-to-1. So once you know this is a half, you match 1/2 to this, and then you realize that pi has, rather than that t has to be pi, so that when you perform this division, you end up with a half. If you are just relying on cosine and sine, then you could have multiple solutions, because you get 0 under sine at 0, pi, 2 pi, 3 pi, and so forth. So that is not too deterministic. We could have multiple points. Anyway, so we want to find this. Let me copy down. So let's start the solution to this. Solution. I'm going to copy r of t, which is cosine of t, sine of t, and t over 2 pi. So the first derivative will be negative sine of t, cosine of t, and of course 1 over 2 pi because the t vanishes. Next, we need to find the magnitude of that. That is going to be the square root of negative sine of t quantity squared plus cosine of t quantity squared plus 1 over 2 pi quantity squared. Here, the negative will vanish after we square cosine squared. So sine squared plus cosine squared of the same angle is going to give us 1. So we have 1 plus 1 over 4 pi squared. We have done this a few times in previous videos, this computation, and it boils down to the square root of 4 pi squared plus 1 over 2 pi, because This 1 becomes 4 pi squared over 4 pi squared. We have common denominator, and we end up with 4 pi squared from the numerator of the 1 plus 1, that's that, over 4 pi squared. Then we split that into two roots, the numerator and the denominator. The numerator doesn't simplify at all whatsoever. The denominator does. Okay, so now we have t of t, which is equal to the r prime. Let's go back to the formula. T is r prime divided by magnitude of r prime. So this is the magnitude of r prime. And we need to divide this vector by this magnitude, or by this scalar, by this number. Now, this is a fraction. So dividing by the fraction, as you well know, is the same thing as multiplying by the reciprocal. So we're going to multiply by the reciprocal of this fraction because we are dividing by that fraction. So 2 pi over the square root of 4 pi squared plus 1, and then multiply by r prime, negative sine t, cosine t, and 1 over 2 pi. Let's label this as equation 1. We're going to come back to it in a moment, well, later, as we plug in t, so we can find our tangent vector. We could do that now. We could plug in the t value and then put that vector to the side, or we can continue with our formulas. I think it is probably a good idea to continue with the formulas. So let's move on. I'm going to put that up here. So because the next thing we need to do is find t prime of t. And so having t there will be handy. Okay, this is a constant, so we can just factor that out of the process of finding t prime, square root 4 pi squared plus 1. And then we just proceed to find the derivative of that. Sometimes this is not a constant. If it is not a constant, then we have to use the product rule for derivatives. So be aware of that. If you're factoring something that is not a constant, then use the product rule. In this case, that is a constant, so we just factor it out. Derivative of negative sine is negative cosine. Derivative of cosine is negative sine. That is a constant, so its derivative is going to be 0. Then we find the magnitude of this vector we just figured. Again, this is a scalar. We can take this sheet away. This is a scalar. So the scalar could, this is a scalar, sorry. That is a scalar, so the scalar could stay out. It is positive, so we don't have to take the absolute value of it. We can just leave it alone. 2 pi over square root of 4 pi squared plus 1. And then we take the magnitude of this vector, negative cosine t squared plus sine t squared plus 0. I'm going to say plus 0 squared. There we go, inside the root. Of course, that is going to be cosine squared after we square because the negative vanishes. So that's in here. I missed the negative there. Anyway, so we end up with, but don't forget though, in your work, I take points off if you miss negatives, such as the one I was missing there. So negative cosine squared plus negative sine squared is going to be cosine squared plus sine squared, and that's of course 1. So this is just 1, and the magnitude is simply 2 pi over the square root of 4 pi squared plus 1. Okay, so now to find the normal unit vector, we take this vector, the derivative of the tangent unit vector, and divide by its magnitude. Now, notice that this quantity is exactly the same as that. So when we divide this vector by its norm, its length, we're dividing, well, we're dividing this quantity by itself, and so we end up with 1. So again, this vector divided by its norm is just going to give us 1 initially because we are dividing those two same quantities. I'm not going to put the 1 down. That's just going to go away, and we end up with negative cosine t, comma, negative sine t, comma, 0. So that is, we're going to label that as equation 2. That is our normal vector. Our binormal vector, let me bring back the formula, is simply the tangent unit vector multiplied with its normal unit vector. We did have the tangent normal vector. That was formula number 1. I'm going to copy it down here. So the binormal vector will be the tangent vector crossed with the normal vector. The tangent vector is this one, 2 pi divided by the square root 4 pi squared plus 1, multiplied with negative sine t, cosine t, and 1 over 2 pi. And then we're going to cross that vector with the normal vector, which we just found up here, negative cosine of t, negative sine t, and 0. So I'm going to proceed with that cross product. A scalar factors out of the cross product, so we can just put it down here. I'm going to use a different pen because I think this pen is not as clear. And then we're going to do the cross product. So we're going to have 0 plus 1 over 2 pi, 1 over 2 pi sine of t. Okay. Then we're going to have 0 plus this, but because this is the middle coordinate, we're going to put a negative 1 over 2 pi cosine of t. Let me verify that. We got 0 plus, yes. And then the last coordinate of the cross product would be sine squared plus cosine squared. So that is going to give us 1. We can factor out 1 over 2 pi out of the vector. And the reason for doing that is because we have a 2 pi here. Square root 4 pi squared plus 1. So we factor out 1 over 2 pi. That way those two will simplify. We end up with sine of t, negative cosine t, and of course 2 pi. Because when we factor 2 pi out of 1, well, we have to come up with the 2 pi so that when we multiply back with what we factor out, we end up with a 1. And then those two simplify. So let me write down the 3 vectors. Well, actually, I'm going to keep them here. This is 3, formula 3. And let me double check with the work I did earlier. Yeah, I ended up with the same formula. So we have the 3 formulas, 1, 2, and 3, for the tangent unit vector, the normal unit vector, and the binormal unit vector for this curve. And now let's plug in the numbers. So let's go back to, so t, big T, at pi. Remember the original problem asks, whoops, example 1, there it is. To find the tangent, normal, and binormal vector for this, the helix, at t equals pi. So we're going to plug in pi. And by the way, those numbers came from plugging in pi into cosine, sine, and t over 2 pi. That's where this point came from. All right, so T of pi, same page. Yep. So earlier here, we found T of T. So we're gonna plug in pi there. Okay, so is 2 pi over square root of 4 pi squared plus 1, parenthesis. Now remember, we're plugging pi. Sine of pi is 0, so we end up with -0 or just 0. -1, because cosine of pi, we're plugging in pi, is -1. And then that is a constant, so we just keep it the way it is, 1 over 2 pi. Our normal vector at pi, so that is formula number 2, the one we labeled as formula number 2. There it is. So there's formula number 2, which we derived. And what we're going to do is plug in pi. So cosine of pi is -1, but then there's an extra negative in front of the cosine, so that is going to give us 1. Sine of pi is 0, and of course 0 again. So that is a nice, neat, that's I vector. And then the binormal vector, at this point you could do two things, by the way. You could use the formula we came up with, formula 3. There it is. I did not simplify this formula. There's the 2 pi's would cancel off. Once those two will cancel off, then we have a simplified formula. Or you could do the cross product of those two vectors. That would be a redundancy, because that's what we did here. We did the cross product of those two vectors, so that would be redundant. Having said that, it is not a bad idea to be redundant in mathematics, because we would be double checking our work. Since we have this formula, let's use it. But again, it's not a bad idea to be redundant, because we are double checking our work. We would be double checking our work. Okay, so those two pi's cancel off. We're still going to plug in pi for t. So we end up with 0, 1, and 2 pi. Yes, because we're dividing by this. I was thinking this vector seems rather large, but it isn't, because we're dividing by this quantity. And so this is still a unit vector. What does that mean, those three vectors? Let's draw a picture of what's going on. Remember our helix. It goes up and it comes back. It's still going up here, and it goes up to here. So it starts out at 1, 0, 0. After one turn, 2 pi, when t is equal to pi, we end up with 1, 0, 1. It goes all the way up to, so this is 1 unit. If this continues back here, we're going to have a point probably about here. This point is the point when t is equal to pi. Yeah. So that point would have coordinates when t is equal to pi. We have the coordinates -1, 0, 1/2. -1, which makes sense, back 0 because it doesn't move on to the right or to the left, and then 1/2. So that is the point at which we're finding the tangent vector, the normal vector, and the binormal vector. So the tangent vector is going not this way or back, because the first coordinate is 0. The second coordinate is -1, which means it's going to the left and up a little bit, which makes sense because this is going around and this is the back of it before we start coming back forward. So right there, the tangent vector is going this way to our left. Yep. it has a slope. It is not moving towards us or away from us. It's going parallel to this plane, and it's going uh, on our left, to our left, and up because we have. So one way to think of this is go 1 and then 2 pi. Boy, that is actually steeper than this picture shows. Um, but that is not the vector, that is the direction. And then by dividing, I'm sorry, I'm looking at the wrong vector. To the left, -1. Yep. And oh no, this slope is correct. This 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 vector shows about this is a small number. This is 1/6. So yes, I was sorry, I was looking at the binormal vector, but I'm drawing the tangent vector. So this is the tangent vector. It goes in the direction of the curve. So if we have a particle that was moving in this motion, and then all of a sudden we just let go by pure inertia with no gravity, then the particle will be moving straight in that direction. The normal vector points towards the bending of the curve, the center of the bending of the curve. So 1, 0, 0 means this vector, but we position this vector starting from here. So the normal vector goes this way, and it points towards the center because from the top view, we have a circle. The top view is really a circle. And if you start here, and now we're on the opposite side, the bending happens towards the center in this case. Yeah. So this is the normal vector. Tangent vector, normal vector, they're both supposed to be 1 unit long. And then we cross the two, tangent normal, to get the binormal vector, which would be pointing not totally up. I was going to draw a vector that was straight up, but that is incorrect because that would be just 0, 0, 2 pi. That would be straight up. So this means that we're going a little bit in the y direction, 1 unit and then 6 units. And so we end up with this, which is making sense because those two vectors are supposed to be perpendicular, those two vectors are supposed to be perpendicular, and this is the binormal vector. All of them are supposed to be unit vectors. They are unit vectors. The reason why I say that they are supposed to be unit vectors is because my picture may seem like, it seems in the picture that the vectors are not of the same length, but they're supposed to be all of the same length. So tangent vector in the direction of the particle, normal vector, the direction of the center of the circle if the particle was going in a circle. The binormal vector would be the cross product tangent versus normal. So you cross them this way. And by the right hand rule, the cross product gives us this vector. So that is a neat example, I think, of finding the tangent vector, normal vector, binormal vector. In the next video, we're going to see how those three vectors are used to come up with planes that are relevant to this curve. So the plane that the curve goes through, and another plane that the curve sort of belongs to. The one thing I would suggest you did was to come up with the equation of a straight line and find the tangent vector. That shouldn't be a problem, but the normal vector should be a problem because there's no bending on the straight line. So do find a straight line. So as an exploration, come up with a straight line. Come up with a straight line R of t and find t, n, and b, tangent, normal, binormal unit vectors. Tangent should be a problem. Here is where you should have, I mean, the tangent vector should be no problem whatsoever. Finding the normal vector, that should be a problem because there is no bending. So try to do that and see what happens. And with this, we'll stop this video now.